Hey, what's up, guys? This is Dr. Vivek Palipuram bringing you the very first lecture of random signals in an online manner. So we are going to start our unit number 3 on continuous random variables. Now, this lecturette that I have posted is going to cover your midterm 2 analysis, and we are going to recap some of the important terms that we have studied in unit number 2, because those terms are going to carry over to unit number 3 when we deal with continuous random variables, and it will be very easy for us to pick continuous random variables once we refresh those terms. So let's talk about your midterm analysis. Drum go roll, guys. There you go. So these are the statistics for midterm number 2. So maximum marks scored in midterm number 2 was 50 out of 50, and I was really very happy with this performance. Not only that, there were several students that were really very close to 50 out of 50, but they happened to make a very teeny tiny mistakes here and there, and unfortunately, they couldn't achieve this milestone, but they were very close to it. I'm extremely happy with the average marks of the class, and that is 44.33. Now, here's what I would like for you guys to do. Try to guess the distribution of marks for the class based on just these statistics, the maximum and the mean. Are you able to do it? You can pause your video here to take some time to think about it. Okay, now I hope you had some chance to think about it. Now the answer is it is not feasible entirely for us to determine what the distribution is based on just this statistic. So let me give you another statistic here. The standard deviation sigma x for the class was 7 marks. Now using these two, can you guess the shape of the distribution? Okay, so I hope you had some chance to think about it. Let me give you some more statistics. The skewness of the class marks was -415. Now, if you recall, skewness is the expected value of x minus mu whole cube. Now, the skewness will be negative if there are few values, if there are few marks that are far below the mean. Those values tend to pull the distribution towards the left. So consider a normal distribution for now. In an ideal world, this is going to be the distribution of the marks, which is perfectly symmetric about the mean. But there are a few values, or there are a few marks in the class that are less than the mean, that are far less than the mean, that are trying to pull the distribution towards this in this way. So there are a few values that are trying to pull the distribution that way. And because of that, the shape of the distribution will be something like this, isn't it? Are you guys convinced? Let me give you some more statistics here. The kurtosis value was 128,000, and kurtosis is defined as the fourth central moment. Now, if there are a lot of outliers in your marks, then that means the kurtosis is going to be really very high. Or rather, a high value or a large value of kurtosis means that there are some outliers. So without further ado, let me show you the shape of the distribution. So this has been the shape of the distribution. And you can clearly see here that the mean is right here. Most of the marks will be about one standard deviation from the mean. So for example, mu minus sigma in this case is equal to approximately 37, and mu plus sigma here is approximately 50 out of 50. And there are a few negative values that are pulling the distribution towards the left. And therefore you have a larger tail towards the left. And these are also the outliers. So if you happen to be one of these outliers, then please come to me, meet your prof, and try to pull your grades up. And I'll totally help you to improve your performance in midterm 3 and in your final exams. So nothing is lost. Even if you have not performed well in your first and second midterms, it's okay. You can still pull up in your midterm number 3, and you can do really well on your final exams. I will totally help you with that, and you can secure high grades in ECPE 127. So let's move on. So in this lecturette, we are going to cover some of the important terms that we have seen in unit number 2. Because these terms will carry over really nicely to continuous random variables, and it will help you understand continuous random variables far better. So those terms are probability mass function, cumulative distribution function, expected value, and variance. So let's recap these terms one by one. So the probability mass function gives you the probability that random variable capital X takes on a very specific value, small x. Essentially, probability that X is equal to small x. Now, probability mass function is a generalized probability function for a given random variable. For some of the named distributions like binomial, the PMF takes a nice math form. For example, for a binomial random variable, the PMF of x is n choose x times p to the x times 1 minus p to the n minus x. That's the generalized probability formula, or the probability mass function for binomial random variables. Now, this function is going to change for different scenarios. For example, if I were to roll a die 6 times, and let's say that I'm interested in the number of 6s, then n in this case is going to be 6, and p is going to be equal to 1 over 6 because it's a fair die. Now, this probability mass function is going to differ for it's going to be different for different experiments. So that's probability mass function. The next theory that we dealt with was the cumulative distribution function, which gives you the probability that random variable capital X is less than or equal to small x. It's less than or equal to small x. Now, there's a very good reason why it's called as the cumulative distribution function. The reason why it's called as a cumulative distribution function is because to find the probability that x is less than or equal to small x, all we need to do is add the PMF values for those x that are less than or equal to small x. So essentially a summation from -infinity to x, PMF of x at y. So essentially what we are doing here is we are maintaining a running sum of probabilities, and therefore it's called as a cumulative distribution function. We are accumulating the values. The next important theory that we studied was the expected value. Expected value is also called as the mean of a random variable, or it's represented by mu, and it's called as average, and there are many other terms. Those all mean the same thing. Those just mean the expected value. Expected value of a random variable x is given by this formula. If you have a function of x, you can find the expected value of that function of x using this formula. And it's a matter of just simply plugging and chugging the values in your calculator. Expected value tells you, or it gives you an indication, what a random variable is going to typically take a value on. Or rather, what value a random variable is going to take for a given experiment. Then we discussed variance, which tells you how far apart the random variable values are about the mean, and the variance of x can be obtained by applying this formula. Variance of x is equal to expected value of x squared minus expected value of x whole squared. So expected value of x squared can be obtained by applying this formula, and expected value of x is obtained by applying this formula. So it's a matter of properly applying these summation formulas and getting the variance. Now remember that the variance has a unit squared. So let's say that I'm talking x in terms of talking about x in terms of marks obtained by a class, then variance of x is going to be marks squared. Now that doesn't tell you a whole lot, because how do you physically interpret marks squared? Instead, we rely on standard deviation, which is square root of variance. So for your midterm number 2, variance of x happened to be 49 marks squared. Now that really doesn't tell me a whole lot, but sigma, which is square root of 49 marks squared, was 7 marks, which tells me that some of the points, or are 7 marks away from the mean. So it is not uncommon for some of the marks to be less than the mean, or 7 standard deviations away from the mean. Okay. So in this class, I just discussed the midterm performance and some of the important terms that we have studied in our previous units in random signals. And those terms are probability mass function, expected value, and variance. Now next, we are going to start our unit on continuous random variables. And there, soon you'll find that this summation term will be replaced by an integration term, because when we deal with continuous random variables, we perform integration more often than the summation. In fact, integration can be considered as summation of countless number of values. So I'm going to stop this lecturette right here, and in my next lecturette, I'm going to post theory and practice examples on continuous random variables, starting with the definition of a continuous random variable. All right, guys. So we will end